Welcome back, everyone. Today I'm going to be going over some additional Laplace things. Specifically today, I'm going to be talking about a bunch of the Laplace operational properties. This is not exhaustive, this is just most of them, and I will do my best to cover what you should look for and how we go about dealing with all of these. So first, that first operational property is called a translation on the s-axis. And what you should look for when you're trying to do translations on the s-axis is something of the form f of t is equal to, or f of t times e to the kt. Specifically, this is multiplicational or multiplicative, and you're looking for some f function multiplied to some e to the kt function. This is going to tell you that you have an s-axis translation. When you go ahead and do that, so then you would go ahead and take your Laplace of both of these. This is going to become the f. So remember, if I'm doing f of t, the Laplace of f of t is going to be f of t. When I go ahead and do this translation, it becomes f of t minus k. So for example, I would see something of the form t cubed e to the 3t. I'm going to take the Laplace of this. I think about it like doing the Laplace of t cubed, which I know is the Laplace of t cubed is going to be 3 factorial over s to the 4th. Then when I do this guy, it's going to become 3 factorial over s minus 3 to the 4th. And so that's how you do it. Feel comfortable to either identify this first and then make the change from here, or just go straight from here to here. It's really up to you when you want to go ahead and do that. Then, of course, whenever we're talking about these operational properties, I also want to be able to identify how I go backwards. And so let's look at the case of something like two s plus 5 over s minus 3 squared. I'm going to want to do the inverse Laplace of this just like I normally would. Now this one's a little bit trickier because I do have a complicated fraction with stuff on top and stuff on the bottom. Remember, whenever I'm doing Laplace or inverse Laplace, I want to make things match my reference table as closely as possible. So I'm going to want to change this. You can, of course, do partial fraction decomposition just like you normally would, which we now have a video if you want to go ahead and check that out. But what I'm going to show you is another little method. It's basically the idea that if I add and subtract the same quantity, it doesn't change what is actually going on there. So I'm going to do the inverse Laplace of this, which is going to be equivalent to the inverse Laplace of s to s minus 6 plus 6 plus 5. And the thing that identifies to me that I'm looking for a minus 6 is that I have a minus 3 down here and a 2 here as well. This is something that becomes much easier to see the more you do it. Then if I wanted to take this Laplace and split it up into 2 Laplace functions, I then have 2s minus 6 over s minus 3 plus inverse Laplace of 11 over s minus 3 squared. This should still be squared. I can then simplify this thing over here because there's a common factor of 2, so that becomes 2s minus 3, and then I end up with, which can cancel to 1 s minus 3 in the denominator, and then I'm looking at the inverse Laplace of 2 over s minus 3 plus inverse Laplace of 11 over s minus 3 squared. This one, they both look very similar, but with the first one, since I just have a straight s minus 3 in the denominator, that's going to be pretty clear to me that it should just be whatever coefficient I have multiplied to e to the 3t. So in this case, I'm going to write my solution right here because I am running out of space to clearly see what I'm doing there on the bottom. This is going to be 2e to the 3t. And then with the second one, again, I need to identify what it is. I see that s minus 3, but because it's not just s minus 3, I can get an idea that there's some s-axis translation here. So that s minus 3 means I'm dealing with some other term being multiplied to e to the 3t. And then if you wanted to go about and do like that intermediate step, I'd be looking at Laplace inverse of 11 over s squared, which is looking like t, and then I also would have a coefficient of 11. So this becomes 11t. I would recommend going through this one a little bit slower, but I want to try and get through as much of this as I can in a reasonable amount of time. So if you need to review how to do Laplace and inverse Laplace, check out the Laplace part 1 video. Okay, so that's the s-axis translation. The next one that we're talking about is another translation on an axis. Now we're talking about t-axis translation. When you see a function that has not had the Laplace transformation applied to it yet, it's going to look something like f of t minus a u t minus a. And if you wanted like to comprehend what this is essentially saying, it's saying that I'm addressing some Laplace that does not have the normal 0 to infinity bound. Remember, Laplace is 0 to infinity e to the negative st of f of t dt. Well, this is saying that I'm looking at something that has been moved a little bit, and that's fine for us. When I go ahead and do that, it's going to become, when I take the Laplace, it's going to become f of t times e to the a s, actually f of the s instead of f of t. So this is after my Laplace transformation. And then going backwards is the same idea. So if I go ahead and do that forward transformation with e to the 3 minus t with this u, t minus 3, you can either add parentheses here or not. There are going to be some cases where some things have the translation applied to it and other things do not. So just keep that in mind. I wouldn't do it here because there's only one term, but sometimes you'll have multiple terms with the translation applied to it. So just watch out for that. This, I could then become negative t minus 3. So then it looks exactly, and that's important because this helps identify the value that I'm actually doing for my Laplace. So when I do the Laplace of this guy, it's really the Laplace of 3 to the negative t multiplied to this e to the negative as. I did drop the negative here. It's always important to watch those negatives. It's something that we can all do when we're doing math. So in our case, this instead of a is going to become 3. So let me go ahead and erase that a and replace it with 3. So then I just need to find the Laplace of 3e to the negative t. And when I go ahead and do that, I have 1 over s minus 1 times e to the negative 3s. Now we get a good idea of what we're looking for when I need to put things back into this form when I do the inverse Laplace. So let's consider the function inverse Laplace of s over s squared plus 9 e to the negative pi s over 2. So the way I would do this is basically just doing the inverse Laplace of s over s squared plus 9, which I know the Laplace of this, or the inverse Laplace of it rather, is cosine of 3t. And then when I'm going ahead and plugging it into my final version, it becomes cosine of 3t minus pi over 2 with that u, and then t minus pi over 2. It's very important to go ahead and add in those additional parentheses, especially in a case like with cosine, because it's specifically the translation with the t, or rather, with the t. So just watch out that when in doubt, add parentheses. but that is how we go about doing this t-axis translation. So I'm going to go ahead and clear. The third type of translation is essentially a translation of a transformation on the integral. And this is more commonly known as convolution. Convolution is of the form or of some form f star. This is typically going to be bigger than just a normal asterisk or a normal multiplication mark, g, and I can consider it as this form f of tau g of t minus tau d tau. And that would give us the actual form of what this produces. The nice thing about this is that the Laplace of a convolution becomes the Laplace of f multiplied to the Laplace of g. Easy peasy. Super helpful. This is something to understand of why this is different than just a normal multiplication. However, it is very uncommon for professors to actually go ahead and ask you to go ahead and compute this. It is not completely uncommon, but just keep it in mind. You would compute the integral just like normal. Okay, now when I get here, let's look at an example. So I have the Laplace. It looks like I don't have a forward, I just have a backwards Laplace. I think it's pretty straightforward how to do it forwards. You would just have two functions being convoluted with each other, and then you're breaking it up into two Laplaces that are being multiplied. And then you do the Laplace of f multiplied to the Laplace of g. Now, if I'm going backwards, which let's look at an example of s squared s minus 1, I can still do the same thing and break it up into two. It's just in this case, it's a little bit more tricky because you need to identify if the numerator is more complicated, what goes with each part of the denominator. This one's pretty straightforward for us where it should be 1 over s squared and the inverse Laplace of 1 over s minus 1. And then this is super straightforward. You just have to remember that technically, because these are now representing t functions, it's not multiplication in between, it's convolution in between. Because inside the inverse Laplace, it's multiplication, so outside the inverse Laplace, it's convolution. Then I can just go ahead and plug in, and so it becomes t convolution e to the negative t. Not too bad. Okay. I'll go ahead and clear. The next one we are considering is a periodic function. The interesting thing about a periodic function is I'm essentially thinking about it in terms of a t translation. It's just a little bit more complicated. So one of the common ones that pops up and it is covered in the book is essentially this function that goes like this. And specifically, we're told it basically has the form of a sine function, which is very helpful to us. And then we're told this is 1, this is pi, this is 2 pi, and all that fun kind of stuff. So the way I would go about describing this is a periodic function can be turned into f of t multiplied to u of t minus a minus u of t minus p, or minus a minus p. Now this gets complicated, right? A is wherever that periodic function starts. So this periodic function obviously starts at 0, but let's say it started at pi instead. So then I'd have pi there. In our case, like I said, our period starts at 0, so I can go ahead and just plug in 0 for a, so it's not really going to change anything. Then I need to identify what p is. P is the length of your period, which is essentially what is ever is repeating. In this case, you can see that if my normal sine function essentially looks like this, my point between 0 and pi is the thing that's repeating over and over and over again, right? I'm not ever getting the thing below. So my period is 0 to pi, or that length of it is pi. You can kind of think about it in terms of trig functions back all the way in pre-cal, and how they have periods of repetition. And the period of repetition is just how long that repetition takes. So this repetition only takes the length of 1 pi, and so you could do any distance. This is pi to 2 pi, but the length of that period is pi, and that's how it's always going to be. Then the last little bit is just identifying whatever your f of t function is. And when you go ahead and identify what the f of t function is, which in our case, because we talked about how this is essentially just the first hump, the positive hump in a sine function, our f of t is sine, just sine of t in this case, because it has a height of 1. Then I'm almost good. I can go ahead and multiply this out. I will point out, if you have this t translation t with nothing added or subtracted to it, I can essentially just ignore it, and it's just a 1 there. So this becomes sine of t minus sine t minus pi u t minus pi. And then we're going to go ahead and take the Laplace of it. I didn't see an example where you have to take the inverse Laplace of it, but this is something that you can recognize as well. And honestly, if you're just being asked to take the inverse Laplace, do the inverse Laplace. Don't even worry about trying to identify that it's a periodic function. You just would take the inverse Laplace like normal. So in our case, this ends up becoming 1 over s squared plus 1, and this one also becomes 1 over s squared plus 1 times e to the negative pi s. And then if you wanted to, you could go ahead and simplify these things. I would just leave it here because this is the form that would be easiest to do the inverse Laplace of. And if you were doing the inverse Laplace, you just stop here. I would say don't even worry about continuing further. Okay. Then I'm going to clear. The last translational property is called the Dirac delta function. Now, there's a couple ways that you can think about that. Graphically, it's essentially the idea that I have something that looks like this, and then I have whatever's going on here. It's up here for a split second, and then it goes down. And so one of the ways that we could go ahead and define this is as f of t, it's specifically called an impulse, is 0 between 0 and t naught minus a, and then 1 over 2a, such that I'm between t naught minus a and t naught plus a, and then 0 afterwards. Basically, the value under this should be 1, and there's a couple ways that you can go ahead and reach it. Honestly, dealing with it like a piecewise function is not how we often see it, but it is good to understand how we get here. So I'm going to go ahead and clear that. Generally, we can kind of treat it the same way as the translational property. It's just this one, I'm just dealing with a delta, with a t minus a. There is no additional f of t minus a function here, so I'm just dealing with this. Then when I do the inverse Laplace sometimes, which will happen when I do the inverse of like a differential equation, if I started with a delta, there are times where I can end up with a t translation instead of just the delta, which is fine. In this case, it just becomes e to the negative a s. and that's all it is. Super straightforward. So if I was looking at e to the negative 2t, and I took the Laplace, negative 2s, it should be negative 2s, and I was doing the inverse Laplace of this, it would become just the delta t minus 2. And that's something to keep in mind as well. If I technically have like a constant here, so this is 2, well, that becomes 2 delta t minus 2. Okay. So that covers all of our translational properties. The important thing to keep in mind with translational properties is these will typically come up when I am dealing with the Laplace of a differential equation, specifically on the right-hand side of the equal sign, and we could see all, some, or none of them mixed together, all kinds of stuff. And so if we can understand how to deal with them alone, it helps us understand how to deal with them in the terms of the Laplace of a differential equation much better. Okay, that's all I have for you right now. There will be another video about Laplace of a differential, and it'll cover just the Laplace of a differential stuff. So I highly recommend combining these things together to get an idea of what things look like. Okay, good luck everyone, and have a nice rest of your day.